right, welcome everybody to my session here at the NLP Summit. My name is Zain. Today I'm going to be talking about how we can scale vector search and keep the costs in check, right? So the talk is titled Scaling Vector Search Without Breaking the Bank. Just a little bit about myself. I work as a senior dev role at Weaviate. I've been working in engineering and in data science and machine learning for about 9 years now. I'm very passionate about AI teaching and education and open source in general. Feel free to connect with me here. That goes to my LinkedIn. I work for a company called Weaviate, and they're a developer. They're the developers of one of the oldest vector databases in the market. They're founded in 2019, raised a bunch of money. Probably the thing that I'm most proud of here is that we've got a whole bunch of open source users here, and the open source product is great. Every time I go to a conference, I learn about a new company that's using the product. So really in this talk, what I'm going to kind of narrow in and focus in on is why do we care about quantization? What even is quantization? Why do I want to compress vectors in a vector database? Right? So really here, the motivation is money. If you compress vectors, if you quantize vectors, you save a lot on memory. You save a lot on the compute that you're going to be using to power your vector search engine, right? So if you have a RAG application, you could cut costs by 80% if you choose to quantize. Right? So really here, the demo that I wanted to show people is if you go to the payments calculator, let's say you've got vectors that are 1,500 dimensional. You've got about, let's say you've got around 11, 12 million vectors, right? So that's about that much per month in vector database costs. If you go here and if you turn on compression, this goes down to 200, right? So it's about a 80%, 70 to 80% decrease in price. And this is what quantization and compression enable. So I'm going to talk about the technology that allows us to do this in the background. And of course, all of these features are available for open source as well, right? The only reason why I show this is to show you the power of quantization and compression. You can use this managing it yourself in the open source product. So the technology is not closed source or anything like that. Okay, so let's quickly go into what is compression. So that's the entire motivation, just one motivational slide, right? So let's talk about compression, and I want to talk about compression from the perspective of images. Right? If I show you this image and I ask you, show me a compressed version or compress this image, one way to do it would be to take all of these different colors and just limit the different shades, right? So notice how the ocean in the background now in this compressed format is not all the shades of blue, but very kind of discrete quantized shades of blue, and you can see the transitions between these states, right? And those are the compression artifacts that come into play when you limit the number of colors that you can choose. This saves on memory because now you don't have to remember multiple pixel values. You only have to remember certain pixel values, right? And so in this case, I've limited it down to about 16 different colors that can be used in this image. And these are the only colors that you'll find on the right-hand side. And you can actually see these colors, right? So that color right there could be that, for example. There's another shade there. You can actually see the colors in the image. And so this limits memory usage, but it also adds a lot of these artifacts. And so we've got this kind of trade-off that's going on. In the perspective or from the framework of a vector embedding, what we need to ask is, how do we do this similar type of compression to vectors? And this will limit the memory footprint, but it will introduce these compression artifacts as we saw in the image, which will reduce the accuracy of our vector retrieval overall. Right? So if you think about how big these vectors are, typically, let's say you've got a vector of 1,000 digits. Every digit here, so each one of these numbers is going to be a 32-bit floating point. So it's going to take up 32 bits. Right? So that's a 32-bit floating point, and then you've got 1,000 of these. So if you do the math, 1,000 times 32 bits, that's about 4 kilobytes per vector. Right? And so all of these have to be in memory for vector search to happen quickly. And so that's going to add up really quickly, right? So if we look at some of the numbers here, if you're using OpenAI vectors, 1 million of these 1,500 dimensional vectors require 6 gigabytes of RAM to vector search over, right? And of course, the requirements are going to be a little bit higher than this because these are just purely the vectors and you need memory for other things as well. If you're taking the same vectors and you're embedding them with Cohere, that's 4,000 dimensions. And so here, the same 1 million vectors are going to require 16 gigabytes at least of RAM. And so the dimensionality of these vectors is increasing, and so your memory footprint is increasing. We need this counterbalancing force to reduce this memory requirement, right? And that counterbalancing force is quantization, is compression. So we'd like these vectors to go from 32 bits down to something smaller, right? One option here is one quantization option that I'll present is an 8-bit quantization where every number in your vector, every dimension, will be turned into a 8-bit integer. And so this process is known as scalar quantization. What scalar quantization really does is, if you think of your signal, or if you think of your vector as in every dimension, it can take up any one of these values across the y-axis here. What scalar quantization is saying is, you know, taking up all of these different spaces is taking up too much memory. I'm only going to allow certain values to be allocated, right? So you can either take 0, or you can take this 2.5, 3.5. You can take these like rungs on the ladder. You can't take up every single value. And so again, notice how the blue signal is different from the green signal. Those are the compression artifacts, but the green signal is a lot more efficient to store in memory. And so that's the trade-off coming into play here. This is pretty much exactly the same as limiting the number of colors in our image, except now our image is not an image, but rather a vector, and we're limiting the number of possible steps that every dimension can take on. And so when you do this, your vector, you can actually see it in the vector. This is the original vector. When I choose to quantize with scalar quantization to 8-bit integers, this is what the output vector now looks like. And so when we ran this to benchmark and see how much trade-off, how much accuracy or recall we're trading off for this gain in memory savings, we get about 75% memory savings when we're applying scalar quantization, because we go from 32 bits to 8 bits, but the recall decreases by about 5%. Right? And so this is on a data set of 100,000 objects that is from DBpedia. So there is some recall, but there is a disproportionate amount of memory savings compared to the recall, right? 75% versus 5%. The next technique that is available and our customers use in production is product quantization. What this does is, imagine these are all of your vectors, right? So all of the black dots here are your vectors, and each vector is connected to some object. It could be a chunk of text, it could be an image. What we're going to do is create these Voronoi cells where each region will capture some number of vectors, and then we're going to learn some centroid for these regions, right? So the white dot here is the centroid for that region, and instead of keeping a distinct representation for each one of these black dots, we're going to use the centroid location to represent each one of these black dots. So in memory, all we're going to keep is a representation that looks something like this. And so now we don't need to store all the black dots. All we need to store is which white dot does that black dot map to, right? And so that saves a lot in memory. But the problem now is that previously we could tell the difference between that dot and that dot, that dot and that dot. But now, after our product quantization compression, all of those dots are kind of overlapped onto this region. And so now they're indistinguishable. Right? And so that is the memory compression artifact that comes into play with product quantization. And so when we ran this type of quantization through the same benchmarker, we got about a 16x reduction in memory footprint. So that's a lot bigger. But again, the price that we're paying for that is also higher, right? So we lost about 17% recall as opposed to the 5% recall for scalar quantization. Right? And so there's always this price that you're paying for saving on memory costs. The third technique that we've implemented and our customers also use is called binary quantization. Binary quantization is this really kind of crazy take which says, how much can we compress the data? How much can we compress the vectors and still get good results, right? So if you think about an image, let's imagine this is our image on the left-hand side, and this is the original image. If we binarize this image, effectively what we're doing is we're going through every single pixel on the left-hand side, and we're saying that pixel can either be a black or a white pixel. right? And when you do that, you get something like this. Right? You're essentially thresholding, and you're only allowing black and white pixels. So you're just turning that image not even into different shades of gray, but rather just a 1 or a 0, right? And that's why it's a binary image. It's a binary decision. It's a 1 or a 0 decision. That's going to take out a lot of information from the image, right? When you look at the same method applied to a vector, it looks the same, right? Imagine you have your original vector where every color here represents a different value. And so the different shades are different values of numbers. When you binarize it, you turn it into this binary kind of barcode-like vector. Right? And so you lose a lot of meaning when you quantize this way. But the advantage is that this requires a lot less memory than this to store. Right? This is 32 bits per dimension. This is only 1 bit per dimension, just 1 or a 0. Right? And so when we use this type of quantization, we go from having vectors that have these continuous values now to vectors that just have, you look at the sign of the value. So if this is positive, that'll be a 1. If this is negative, this will be a 0. Right? So if your vector looks like this before quantization, then after quantization, it's simply a 1 for the positive, 0 for the negative, 0 for the negative, and then 1 for the positive here. Right? And so when we ran this through our benchmarker, we got now a 32x reduction in memory because we're going from 32 bits down to 1 bit for every dimension. But we lost a lot of recall, right? So you can as you can imagine, the image, once it's binarized, once you turn it into a black and white image, it doesn't look the same. You lost a lot of the meaning, and as a result, we lose a lot of recall when we're trying to compress this way. Right? And so, what in practice, what this might mean is when you're trying to search for something, the objects that come back might not be relevant, right? 65% of the times, you're not retrieving the relevant objects. So you're getting 65% relevant objects, and then 35% of the other objects might be irrelevant to your search query. Okay? And so that's pretty bad. If this was the end of the story, then quantization wouldn't really be useful in all cases. But that's not the end of the story, right? So the last part of the story, I'm going to talk a little bit about adaptive retrieval. Right? So adaptive retrieval is this hero that comes to save us and prevents all of this loss and recall from actually happening in production. Right? So we've got kind of these two forces that are going, one is going for us and the other is going against us, right? We'd like to save on memory costs, and that's that we can do that with quantization. The trade-off, the problem is that if you quantize too much, the quality of your vectors goes down, and so the actual relevance of your search engine decreases. And so adaptive retrieval allows us to answer this question of why can't we have both, right? Adaptive retrieval gives us a way to have both of these things, and it might sound magical. It is magical. So let me talk about it. Before I kind of unveil how this is possible, I want to tell you guys a story. And so the story is about a fisherman, and the fisherman is kind of dreaming about this green salmon, right? The fisherman, all he cares about is catching this green salmon. So what he does is he gathers a bunch of his friends, and then they go out to search for this green salmon. The problem is they don't exactly know where the green salmon is, right? So they can't really throw in a fishing rod and wait for the green salmon to come to them. So what they do is they throw out a bigger net in the approximate area where they think the green salmon is. Right? And then they catch a whole bunch of fish, and they're hoping that somewhere in there is the green salmon. And then what they do is they look through these fishes one by one, and then they narrow in to the location of the green salmon. Right? And so here, even though the fishermen didn't know exactly where it was, they did a big enough retrieval. They threw a big enough net to approximately catch the green salmon, and then they spent some more time to wade through it. And then whatever was not a green salmon, they threw it back into the ocean, and then they just caught the green salmon. And this is effectively what adaptive retrieval is telling you, right? This is what it's doing for you. You don't know where the right vectors are because they're compressed and they're kind of fuzzy. But if you kind of overfetch and catch a lot of them, then you can look through them and find the right ones. And so if I ask you to find the green salmon here, like this is our query vector, and I want you to find the closest blue vectors that are close to my query vectors, those are going to be the green salmon. It's really easy, right? You can just go ahead and say, okay, those are your green salmon. Right? But when you, in uncompressed vector land, this is easy because all of the blue dots are super easy to see, right? In compressed vector land, the blue dots look something like this, right? There's all sorts of artifacts, shades. You don't know which ones are real. Some of these are illusions. Some of these are not even real. Some of these are not even in the right location. So you've got all of this kind of haze and noise around. So now it's not easy to say what are the green salmon and what are not. Right? What are the closest objects and what are not the closest objects. So what we're going to do is employ a strategy that the fishermen employed. We're going to throw out a much bigger net, and we're going to say, because we don't know exactly where our candidate vectors are, our candidate objects are, I'm going to throw out a huge net around the query vector, right? So I'm going to throw out this huge net and I'm going to catch everything. I'm going to assume everything in there is a green salmon. And that's my first try. What I'm now going to do is I'm going to remove a little bit of the noise from the smaller candidate set, right? So I'm going to eliminate everything that's outside of this net. So all of that is gone. And then I'm also going to remove the noise from these vectors. And so how this happens in practice is I have the uncompressed vectors on disk, uh, and I read those into memory in an uncompressed in their uncompressed format, right? So I remove noise from the in-memory vectors, and then I do another retrieval. I throw out another net, right? So I adapt this. So now I throw out another net. This is my second try. I'm hoping to get closer and closer to the candidate vectors, the green salmon here, and then I do the same thing. Now I throw out everything that's not colored in green here, and I try to remove the noise around associated with these green vectors. Right? So when I do that, I get this type of approach. And then when I do a third try, now I've approached at the exact correct kind of vectors that I would have gotten if I hadn't compressed them at all. Right? And so this is really the approach of adaptive retrieval. What we really want to do is start off, throw out a bigger net, overfetch, and then once we've got our candidate vectors, we want to read in a less compressed or completely uncompressed version of their format from disk into memory, so that we're not initially storing them in memory, and then we re-rank, right? And then we can do multiple sets of retrievals, or you can just do one retrieval and read them fully into memory in one go. But the advantage of this is that now you can store the compressed vectors in memory, and when you do retrieval, you can read read a smaller subset of the ones that you're interested in from disk into memory, fully uncompressed, and then re-rank and rescore to get that recall that you initially would have lost if you hadn't rescored on the uncompressed version. And so when you do this in practice, you can pretty much compress vectors without paying any cost for the loss and recall, right? So on this graph here, you have recall on the x-axis. Higher is better, 1 is the best. And then you've got QPS, the speed of how many queries you're serving per second. So up and to the right on this graph is better. Right? And the orange dotted line here shows you scalar quantized vectors, whereas the blue line here shows you the uncompressed vector formats. And so in this case, scalar quantization is strictly better than running uncompressed vector search, right, for this data set. And so here, there's no reason why you would want to run uncompressed vector search, right? You get similar patterns for binary quantization and product quantization here. Here it's not, so depending on your data set, you might get outperformance or underperformance, but the code for this is open source. You can look at chaos engineering pipelines and ANN benchmarkers at Weaviate GitHub, and you can run this on your own data set to determine what type of quantization works best for your data. But you'll find a type of quantization that we've implemented in the open source Weaviate version that'll work good for you. And then you can just use that and you can cut down on memory requirements and costs by 80% by enabling one of these and configuring Weaviate to run with them. Right? And so notice how here the green line is almost always better than the orange line is almost as good as the green line here, the uncompressed HNSW. But notice the memory requirements. The green line takes 6.5 gigabytes, whereas the other two lines are taking only a fraction of the memory. And so this is how that 80% reduction in price happens in that pricing calculator that I showed at the beginning of this talk. Okay. So now we can go into Q&A, and I'll be in the chat to answer your questions. Feel free to connect with me if you have questions after the talk. And if you want to learn more, feel free to follow that QR code. Thanks, everybody.